Welcome back to Polymer Science and Engineering. In this recording, I will continue to talk about some other concepts in crystallization, namely the semi-crystalline polymer, the phase transition, and the equilibrium considerations for melting and crystallization. So in the semi-crystalline polymer, we are concerned about the microstructure, the morphology, and its mechanical properties. Why? Because, as I mentioned early on, all polymers that are used in the industry are crystallizable, and they are all semi-crystalline polymers. So how do you get the microstructure of semi-crystalline polymers? From crystallization, which is a process, which is a combination of two different processes, nucleation and growth lamella. Let us take a look at nucleation first. So in nucleation, what you have is you have two different processes, heterogeneous nucleation or homogeneous nucleation. In heterogeneous nucleation, it arises from the surface of impurities, whereas for homogeneous nucleation, the aggregation of the nuclei comes from polymer segments below the melting temperature. Now, the number of nucleates in homogeneous nucleation depends on the cooling rate of the polymer. If it's fast, you have less nucleates. You have less nucleates. If it's slow, you have more nucleates. Now, above a critical size for this aggregation of polymer segments, what happens is the free energy of the system will have a net decrease. If it's below the critical size, the polymer aggregation is reversible. So for nucleation to happen, you need to have intact ordered regions after melting. And this is the dominant effect in bulk crystallization. What about the growth of lamella? Crystal lamella can grow through adjacent reentry or random reentry, which I've described in the recording for Introduction to Polymers, introducing to you the switchboard reentry model. So once you have random reentry, what happens is the tendency for amorphous regions to form would be higher. For adjacent reentry, you have a smooth, regular chain fold or a rough fold surface. Now, you remember one of the key parameters that actually impact melting temperature is chain length. The longer your chain length is, the lower your Tm is. And Tm is a direct reflection of the behavior of the largest crystallites at the highest possible temperature, right? And this is because long chain lengths cannot be packed nicely into a crystal lamella. In terms of length and breadth, yes, you can pack more chains together, but in terms of thickness, because they are so long, once they start to come back into the structure, you may get a random reentry model or a rough fold surface. And when that happens, you have more amorphous regions. So in the polymer itself, the connections between different crystalline lamella or amorphous regions is this thing called a tie molecule. And the presence of tie molecules then dictate the mechanical properties of your resulting semi-crystalline polymer. Now, your crystal size can be affected by processing as well. For example, if you use melt crystallization, what happens is your supply of polymer chains or polymer segments is significantly higher. This results in long ribbon-like folded chain structures, which is your lamella. Crystallization rate is faster, and As a result, your growing lamella are close to each other. There is a possibility that different parts of a long polymer chain can be incorporated into different crystallites, which are typically the size of 100 microns in diameter. Another way to make crystals is dilute solution crystallization. Now, in this process, what we do is you usually have a dilute monomeric or polymeric solution, and then crystal starts to grow. Therefore, the polymer segments are significantly lower. As a result, you form plate-like single crystals at very slow rates. The size of these single crystals can be about 15 micron in size and about 150 angstroms thickness. Other than the microstructure, we are also interested in the morphology of semi-crystalline polymers. Now, the morphology of semi-crystalline polymers can be categorized into crystallization effects and aggregation of crystallites. Let us take a look at crystallization effects first. Depending on the fabrication method, if you use methods such as extrusion, fiber spinning, or injection molding, that means you're applying stress to the system to obtain chain orientation. You have elongated crystals aligned in the flow direction. The orientation along the long crystal axis would then provide nuclei for growth of a folded chain lamella. The molecular axis of this folded chain lamella is parallel to the fibril. Resulting in a row structure or row nucleated structure. Now, another type of fabrication method, which is to use heating to form your polymers. What will happen is you're actually stretching your polymer between the TG and DM, and this breaks the lamella, forming folded chain blocks, which are connected by microfibrils, which are about 60 nanometers to 2 micrometer long. These microfibrils are between the blocks, which are your crystal lamella, and your amorphous regions, which could include the tie molecules, the chain ends, and the chain folds. The aggregation of crystallites can occur through this process shown here. First, you have a sheath-like nuclei, which is essentially similar to a rectangular rod. And on top of this tree trunk, you start to form a canopy resembling branches, containing branches. Once this canopy grows wide enough to come into contact from both ends in the middle, you form a spherulite. And these are basic units of semi-crystalline polymers. Now, the morphology depends heavily on the crystallization rate as well, which is the cooling rate. If you have a fast cooling rate, what will happen to your polymer is it will have dynamic properties. For example, if I freeze polymer chains in position, what will happen is there's free volume in between the polymer chains, and this free volume will start to be reduced over time, and you will have gradual embrittlement. Another side effect of dynamic polymer properties is possible secondary crystallization, especially when you have low molecular weight matter like stabilizers, catalyst residues, comonomer units, and branches in your material. So what happens is, over time, these materials will be separate, this low molecular weight matter will be separated out from the polymer chains, and then you may form secondary crystallization, which could also lead to gradual embrittlement. Other effects of this low molecular weight polymer is causing polymers produced from slow crystallization rates to become brittle as well. Even though such polymers are made from a system with few nuclei and large ferrolites and with lesser tie molecules, and because they have lesser tie molecules, they are also more brittle as well. Now, the term brittleness and strength, they are all related to the mechanical properties of semi-crystalline polymers. Interestingly, the mechanical properties of semi-crystalline polymers are anisotropic. So along the molecular axis, there are covalent bonds, which gives the semi-crystalline polymer its strength and stiffness. Modulus in the chain direction can reach 200 gigapascals for polyethylene, but transversely across the molecular axis, you have weak intermolecular cohesive forces. This results in